Finding G using a pendulum. Right, this is a really nice little experiment that you can do using a setup of apparatus like this on the right here. You've got a meter stick which is pinned to a surface at the back there. There's a pin there, and the meter stick can swing like a pendulum, and you've got two pulleys and you've got a weight. Now let me give you an idea how this works. Right, a meter stick, if you pin it at one end, it can work like a pendulum. It can swing backwards and forwards. If you pull one side up and drop it, it's obviously going to swing all the way to the other side, and then it'll swing back, and so you get a little pendulum. Now obviously if that swings all the way from here to there and back, we call that one full swing. Now the time taken for that one full swing is known as the period of the pendulum, right? And obviously you can break that up into little sections. First section, second section, third section, fourth section. So one full swing can be broken up into 4 individual pieces, assuming in the middle here is where it would be hanging vertically. Okay, so what we do in that little setup early on, we have a weight at the top here, and we rig it up so that the instant you drop the pendulum, you also drop the weight. You obviously have this thing tied to the back of the meter rule. You cut the string, and when the plumbob the weight starts to drop, the pendulum starts to drop. And usually if you get it set up nice, they're going to crash somewhere around here. And that basically is the experiment. If you can get it to work, what you do is you dirty this thing, or you put paint on it or something that'll come off, and when it smacks the meter rule over here, you have some paper on the bottom here that you get a mark, and you can get a rough estimate. You can get fairly accurately the distance this thing has fallen. So you can measure that distance. You obviously measure this before you drop the weight. That gives you delta x, and then you just need to get the time that the pendulum takes to go from there to there. Now thankfully pendulums don't change, the period is fixed as long as you don't change the length of the pendulum, and we're not going to change the length of this one. So after the experiment, or before it, you can then let this pendulum swing without the plumbob and let it swing backwards and forwards, and you can time one full swing, and then the time from here to there would just be a quarter of a swing. It's more accurate actually to time 10 full swings and then divide it by 40, because then this little bit would be a 40th of the swing of a pendulum. So here's your apparatus setup again. You got the string around the back there, and we usually burn it over here with a candle. You burn it over there. Plumbob drops, smacks the pendulum over here. We've measured that. We measure that distance then on the meter rule, because you measured this to start with. And then you take your pendulum and you do 10 swings and you time it and you divide it by 40, and you go through these steps. So the cotton is burnt to release the plumbob or the weight. The vertical distance is then measured. The distance fallen takes 1/4 of an oscillation of the pendulum. That's that distance there. And the readings you have to take is just the time and the distance. And we've got this equation from equations of motion. Delta x is equal to vi delta t plus half at squared. Now vi, since the plumbob wasn't moving to start with, that is 0. So this section falls away. You measure the time for 10 complete oscillations. Here's an example which I actually did with a class of mine. The time for 10 oscillations was 17.65 seconds. Obviously we divided that by 40 because we're only working with a quarter of one oscillation, and we got 0.441 seconds. So we put that into this equation as the delta t squared. This will fall out because vi is 0. And delta x we can put in there because we measured that. The distance fallen from there to there was just almost the full length of a meter rule. It came out to be 0.81891 meters. Put those values into the equation, rearrange this formula for a. You take the half to that side, it becomes a 2. So you get 2 times delta x. 2 times delta x over here. And then obviously you'd have to divide through by delta t squared. So you've got divided by delta t squared. There's my delta x from the 0.891. There's the 2. There's the time, which was 0.441 seconds. We're dividing by it, and you do all that maths, and you end up with 9.16 meters per second squared. Not a bad value for the value of accepted value of G, which is 9.8, using a very simple set of apparatus. That's how you can measure the value of G using a plumbob. We didn't quite get 9.8, but it's close enough.